Math Instruction Common Core Algebra 1 lesson. I'm Kirk Weiler, and today we're going to be doing Unit 11, Lesson number 6 on piecewise linear functions. This is our last demonstration video in the Common Core Algebra 1 line. By the fall of 2014, we plan to have 100 videos for the 100 lessons and the 100 homeworks that we're offering as part of this curriculum. As always, you can find the worksheet and a homework that go with this lesson by clicking on the video's description. As well, don't forget that on this worksheet and all other worksheets that we'll have videos for, we're going to have a QR code that can be scanned using a smartphone or a tablet and take you right to one of these videos. All right, let's get into it. Piecewise linear functions are really kind of cool, as all piecewise functions are. The assumption that I'm going to make going into this lesson is that you understand how to graph a line, that you are familiar with and you're comfortable with anything that looks like y equals mx plus b. That you know that m is the slope and that b is the y-intercept and that you can interpret them. Now, a piecewise linear function is simply a function whose rule is more complicated, right? And it consists of multiple linear equations. In other words, we're going to have more than one of these things. So, for instance, let's say we had 2x plus 6. Now remember, you can think about this as y equals 2x plus 6. What would that be? It would be that line, right? It'd be a line with a y-intercept of 1, 2, 3, 4, 5, 6, right? And a slope of 2, meaning that if we go to the right, 1 will rise 2. For every increase in x of 1, we have an increase of y in 2. All right? But maybe then we also have the rule negative 1/3 x plus 6. So that's that line, right? Again, a y-intercept of 6. But now for every 3 units that we go to the right, we end up going down 1 unit. Okay? Now, that's not a function, not the way it currently stands, because if I were to go to something like negative 1, what I would find is I would find 2 outputs for that given input. And we know that that violates the fundamental idea of a function. So there's something extra in every piecewise function. There's an interval that tells you what x values the rule applies to. So for instance, the rule 2x plus 6 only applies from x equals negative 4, 1, 2, 3, 4. It only applies from here to x equals 0, 1, 2, 3, 4. We're up here. So we literally get this chunk of the number line. That's what we get, right? And it's sitting right there. Notice the 0 is filled in, and so is the negative 4. On the other hand, maybe negative 1/3 x plus 6, maybe that's a rule that goes from x equals 0 to x equals 6. 1, 2, 3, 4, 5, 6. So it just goes out to here, giving us that line segment. Now, ultimately, our domain for this function, right? Remember that term? The domain, right? The domain from this function simply goes from x equals negative 4 to x equals positive 6, right? So there's extra material on this graph that doesn't need to be here. In fact, that's it. In fact, let me clear out all the excess text, and there's our function. Really, really beautiful, going from an x value of negative 4 up to an x value of positive 6, right? It's just a more complicated rule because it says, hey, follow this linear equation when the x value or the input comes in here, and follow this linear equation when the x value comes in here. All right, I'm going to clear all this out, and we're going to go on to the first real problem. Okay, I'm going to switch back to blue. That's the one I like to write in. And this is a really nice applied problem that is a great example of a piecewise function. So here we go. Now, this entire scenario is about a boy named Mateo walking to school and then walking home. And what we're going to be doing is we're going to be tracking Mateo's distance from home as he walks to school and then unfortunately has a trip back. And the first thing that we're going to be asked to do is to draw a graph of Mateo's distance from the home on the grid provided. We're going to do that as we read through it. For instance, we're going to start Mateo at his house, so we're going to have that point. It says Mateo is walking to school. It's a nice morning, so he's moving at a comfortable pace. After walking for 9 minutes, that's right here, right? After walking for 9 minutes, he's 6 blocks from home. So he's right here. In other words, this point lies on here. Now, if Mateo is walking at a constant rate, then what that means is that these two things are going to be connected by a line. Now, you should do that with a ruler. What I'm going to do is use a drawing utility on this program. So I'm going to connect those with a line. Okay? Now let's find out what Mateo does next. He stops. That's important. He stops. He doesn't move. He stops to answer a text on his phone from his mother. After 5 minutes standing still, he walks home quickly in 6 minutes to get a paper he forgot for school. Okay, so let's think about this for a second. Okay, at 9 minutes, he's 6 blocks away from home. Let me write that down. Then he stops for 5 minutes. So 1, 2, 3, 4, 5. Now think about this for a moment. During that entire time that he stopped, he remains 6 blocks away from home because he stopped. So in fact, what we have there is we've got a horizontal line. Right? We've just got something that looks like this. Okay? Then he walks home quickly in 6 minutes. So 1, 2, 3, 4, 5, 6. He walks home, which means after 20 minutes, he's 0 blocks from home again. And we can connect this with another line, and that's Mateo's graph, right? Or more appropriately, that's the graph of Mateo's distance from home. So now if I said any point in time, right, if I said, hey, how far was Mateo from home after, let's say, 3 minutes, right? You'd be able to say, oh, Mateo was 2 blocks from home. If I asked you how far Mateo was from home after 12 minutes, well, you'd come out here and you'd say, oh, Mateo was 6 blocks from home, right? I said how far was Mateo from home after, let's say, 17 minutes. You could come up here, 1, 2, 3, and he would be 3 blocks from home. So you can give me Mateo's distance from home if I give you any time between 0 and 20. So now let's start doing some formulas. Letter B asks us to determine a formula for the distance that he is from home only on the time interval 0 to 9. So that's on this time interval, 0 to 9. Now notice what we've got is a line. So we've got something that's going to have an equation like y equals mx plus b, right? One thing that we should notice about this line is it goes through the origins. The y-intercept is 0. So our only issue is what m is. Now, I'm going to try to really phrase this in terms of distance and time, right? Normally, we think about m as the change in y over the change in x, but we're going to say it's the change in the distance over the change in time. One thing that we could say is well, Mateo walked 6 blocks in 9 minutes. And if we reduce that, we'd get 2/3, which is really quite cool because look at that slope right here, right? If I go over 3, I go up 2. If I go over 3, I go up 2. Over 3, up 2. So in fact, Mateo's distance is always 2/3 times his time in that interval, right? For that interval, that's his distance versus time. Let's take a look at the interval that goes from 9 minutes out to 14 minutes. That's this chunk. Now I want you to think really hard. If you pick any time in that interval, how far is Mateo away from home? Well, I hope you said 6 blocks, right? It doesn't matter what time we pick. Mateo is always 6 blocks from home. So strangely enough, that's his equation, d equals 6. Now, I know that doesn't almost even seem like an equation, but remember, things like y equals 5 and y equals -2, these are examples of horizontal lines, and that's exactly what we have here. We have a constant distance, distance equals 6. Okay, now comes the bad boy. How do we come up with this equation? All right, well, look, we've done a lot of practice on finding equations of lines over the course of this course. So one thing that's always nice to know when you come up with the equation of a line are 2 points on the line. So what I'm going to do is I'm going to take this point, which is at 9, 14. Oh, I'm sorry, that's wrong. It's good to make mistakes every once in a while. which is at 14 comma 6. I don't know where I got the 9. 14 comma 6. And I'm going to take this point, and be careful about this, which is at 20 comma 0. And I'm going to use these two to figure out the equation of my line. All right, so first let's figure out our slope. The change in d over the change in t. Now we're going to come up with this and then we're going to verify it on the graph, but let's see. The change in the distance would be 0 minus 6. The change in time would be 20 minus 14. That would give me negative 6 divided by 6, and that would give me a slope of negative 1. That's exactly, by the way, what's happening, right? We're going down 1 to the right 1, down 1 to the right 1. That's definitely a slope of negative 1. So right now, right, what do we have? We have d equals negative 1 times t plus b, right? We know our slope, it's negative 1. We need our y-intercept. But that's tricky because that's way up. Whoops, I can't even get it in on the computer screen. It's way up here, right? So what we're going to do is we're going to pull a trick that we've often pulled. We're going to take one of the 2 points, I'm going to use this one, and we're going to substitute it into the equation. I'm going to put 6 in for d. I'm going to put 14 in for t. And the only thing that's left is b. So I'll get 6 equals negative 14 plus b. If I add 14 to both sides, I'll find that my b is 20. So my distance will be negative 1 times t plus 20. There it is. A lot of times that negative 1 wouldn't be written. It would just be written as negative t plus 20. One of the nice things about this equation is you can check it. So for instance, if I put t equals 14 into this equation, it would give me d equals 6, which checks. If I put t equals 20 into this equation, it would give me d equals 0, which checks. So this is a really good example of a real-world situation that can be modeled with a piecewise linear function. It's just one function, but the key is it has different formulas for different periods of time. 0 to 9 has one formula, 9 to 14 has another formula, and 14 to 20 has a separate formula. All right. So I'm going to clear out the text, and then we're going to go on to a more standard problem of graphing. Okay, here it goes. All right, let's move on to the next page. So exercise 2, right, very kind of stock type of problem. We're going to clear the page more than once. We're given a piecewise linear function. Here it is. And we need to graph the function. All right, now I'm going to show you the way that I do this. One could certainly create a table of values, but again, I'm going to go on the assumption that you've been in the course long enough that you know how to graph a line that has this form, all right, without creating a table of values. If you have to create a table of values, please do. So here's what I tell my students. I say, okay, take this line, y equals 2x plus 4, and don't worry yet about this interval at all. Just don't even worry about it. Okay, so what I'm going to do is I'm going to go 1, 2, 3, 4. All right, I'm going to plot that. Okay, I'm going to use the slope to go, the slope of, what is it? The slope of 2 to 1 to go to the right 1 and up 2, or down 1 into the left, or sorry, down 2 into the left 1. I'm going to plot these points. Give me just a second. All right, and now what I'm going to do is I'm going to actually draw the line in, but I'm going to draw it in dashed. So I'm going to let you in on something, right? You've seen this before. Whenever something is dashed on a graph in mathematics, we sort of consider it not to be there, all right? Think about graphing linear inequalities, right? Where you did the shading. If the line really wasn't there, you dashed it. So I'm just dashing that line. I'm not committing to it. Let's take a look at y equals 6 minus x. Now this is one that a lot of people will have struggles with unless they rearrange it like this. Right? In this case, we can identify the slope as negative 1 to 1 and the y-intercept of 6. So 1, 2, 3, 4, 5, 6. And we'll go down 1 to the right 1, down 1 to the right 1, etc. All right. In this case, we would get this line, again dashed. Okay. Once I have my 2 or 3 or however many linear functions graphed, that's when I start paying attention to these intervals. In fact, I'm going to kind of like wipe that out, and I'm going to redo that, strangely enough, in red. Now I'm going to pay attention to these intervals. All right, so let's take a look at this guy. Let's go out to -4 on the x-axis, and let's go down to this line. This is where our function starts, and that's where it stops for that formula. Now notice how there's an equals in both of those. Because of that, I'm going to actually fill in this dot. Oh, am I going to fill that dot in? Okay. And then what I'm going to do is I'm going to connect this with a straight line. Okay. Now let's take a look at the other interval. This one goes from 1 to 5. So there's 1. Circle this. And 2, 3, 4, 5. And I'm going to circle this. Now, notice that this one doesn't have an equality on it. That means we have to leave it out. But this 5 does have the equals there. I'm going to color that in. So now what I'm going to do when I actually graph my function is I'm going to leave that as an open hole. See, that open hole tells me that this point is not included. Point not included. Now, I don't have to go back and erase the dashed lines. I can if I want. A lot of students like to do this. Oh, I want to clean it up, do this kind of business. That's quite all right. But remember, the dashed line really isn't there. So you don't have to do that. All right, let's take a look at letter B, the range of the function. I'm going back to blue. Gotta get me back to blue. The range of the function. All right, pause the video now. See if you can remember what range is, and if you need to, do a little Google search on it. All right, the range of a function is the set of its outputs. Now, there's way too many of those to list here. Right? Outputs are y values. So here's what I want you to do for me. I want you to look at the graph, and I want you to try to figure out what the minimum y value is on the graph and what the maximum y value is on the graph. Okay, go ahead and do that. All right, let's take a look. Here's the lowest point on our graph, and if we come over to the y-axis, we find that it is 1, 2, 3, 4, or -4 as our minimum. This is the highest y point on our graph, and if we come over, it's at 1, 2, 3, 4, 5, 6, so maximum value is 6. We do hit every y value in between because this line is nice and continuous. So we can write our range in one of two ways, actually more than one of two ways, but these are the two ways that I prefer. We can say, well, it's all y values between -4 and 6. Notice how those equalities or inequalities are written. Or if you've learned about interval notation, as our students have, you can write it like that. Remember, those square brackets, if you've used them, means that the -4 and the 6 are included in the range, are included. If they were excluded, then we would use the parentheses. But I'm going to get rid of that for right now. If you haven't seen interval notation, don't worry about it. It just means that your school's not using it. That's okay. That means you're probably using this. All right, I'm going to be clearing out the text, so pause the video now if you need to. Okay, here it goes. All right, let's go on to the next problem. So there's two things that we oftentimes do when we have equations and graphs. Many times we take equations and we translate them into graphs. That was exercise 2. Exercise 3, we're going to go in the opposite direction. This is often the harder thing for students to do. But we want to be able to do it, especially with piecewise linear. So let's take a look at this piecewise linear graph. Now this one actually looks a lot like Mateo's distance, all right? But I think it's actually going to be easier to come up with their equations. What we're going to do is we're just going to come up with the equation for each one of these 3 distinct line segments, and we're going to start by coming up with the slope of the line segments. I'd like you to pause the video right now and see if you can come up with the slope of line segment AB, line segment BC, and line segment CD graphically. Try to do it without doing any calculations. Pause the video now. All right, let's go through it. Now, please note that line AB clearly has a positive slope, line CD clearly has a negative slope. You should be able to tell that just by looking. Now, my claim is that the slopes on these are very nice, and in fact, for AB, I can note that for every 2 units that I go over to the right, I go up by 3. Notice that's consistent, 2 to 3. So in fact, the slope of line AB is 3/2. Remember, always rise over run. Slope of BC, well, that's just the slope of 0, right? That's a horizontal line. There is no rise whatsoever. Now CD, notice here, again, it's the same idea. I go down 1 for every 2 I go to the right, down 1 for every 2 I go to the right. So its slope, and this is very important, is a -1/2. Very important that you have the negative on there. Okay, y is decreasing as x increases. That's what a negative slope means. Let's take a look at letter B. All right. It says, now find the equations of the lines that passes through each of the following pairs of points in y equals mx plus b form. I'm going to actually erase these right now. Where applicable, how can you find the y-intercepts using the graph? So this is kind of neat. With Mateo's distance, it wasn't really possible to figure out y-intercepts really based on the graphs. But here, we actually can. Watch what I'm going to do. Let's say I took a ruler and I did this, right? You can actually extend that line, and you can tell, whoops, apparently you can extend that line too. But you can extend that line, and you can tell what the y-intercept of AB would have been. It would have been 1, 2, 3, 4, 5, 6, right? So we can actually write out the equation of AB because we can figure out its y-intercept from the graph. Right? Its equation is y equals 3x plus 6. Now BC, that should be very easy because it's a constant, right? It's a horizontal line. It's got the equation y equals 3. CD, we can pull the same trick that we pulled on for AB. In fact, I'm going to get rid of that red line so we don't have to see it anymore. And I can extend this line. Of course, you could just do it with a ruler. And I see that its y-intercept is 1, 2, 3, 4. So CD will have the equation -1/2x plus 4. Okay? So now, in letter C, we're going to put these 3 equations together to write the formal, piecewise definition of the function. I always love doing this because it allows me to use the giant curly brackets. F of x equals, here we go. Let's just write down our 3 formulas first. 3/2 x plus 6. 3, I know that seems weird to say that that's a formula, but it is. And -1/2 x plus 4. Now what we have to do is decide on those x intervals. So let's go back to the graph, and I'm going to go back to red. Let's take a look at AB. 1, 2, 3, 4, 5, 6. AB starts at -6, and it goes to -2. Now the question is, what do we put in here? Honestly, there's a lot of right answers. I'm just going to put less than. Okay? So I'm going to have it apply all the way up to -2, but not at -2. I'm going to actually have this formula take over at -2 and go to +2. And again, I could have an equal sign there, but I'm going to leave it off. Then finally, I'm going to have this formula take over at 2 and go all the way to 3, 4, 5, 6. And I have to include the 6 there. To be honest with you, you have a lot of play in this function on where you put the equality signs here. Because this function is what's called continuous, there's no gaps. We don't have a situation like this going on. See, in a situation like this, we'd have to pick this one as the one that includes whatever x value these two are at. All right, let's take a look at letter D. Letter D asks us to find the 1, 0 of this function algebraically. Now, let's pause for a second before we read the rest of it. A 0 is also known as an x-intercept. It's a place where the y-coordinate of the function is equal to 0, right? That occurs at only one location, right there. In fact, let me really highlight it. Let's go for with a totally different color. Let's go green, right? There is our 1 x-intercept, okay? And we're going to find it algebraically. Now, the way that you find zeros is by taking the function and setting it equal to 0, but we've got 3 chunks of the function. We only want the one that applies from -6 to -2. And that's the function 3 halves x, or I'm sorry, that's the equation 3 halves x plus 6. So if I set that equal to 0, that's why it's called a 0, and I solve, right? Subtract 6 from both sides. We'll have 3 halves x equals -6. I always find the easiest way to solve an equation like this isn't by dividing by 3 halves. That seems awfully confusing to me. I end up multiplying by 2/3, do a little bit of division, and I get x equals -2 times 2, or -4. And of course, that's exactly what the graph shows me, right? -1, -2, -3, -4. Excellent, right? All right, there's a lot going on this page, a lot of work going on. So I'm going to clear out the text. You pause the video for as long as you need to, copy down anything you need to, and really think about what we did here. All right, let me clear it out. Now this problem is going to continue on the following page. What I did was I wrote down the function again so that we'd have it at our disposal. Let's take a look at letter E. Read over that for yourself for a minute. All right, let's go through it. Why does setting the formula for this function that applies from 2 to 6, that's this one, why does the function that applies from 2 to 6, why does setting that equal to 0 not produce a viable 0 of the function, a viable 0? Maybe we don't know what that word means. Maybe we do. We've gone over it in our text before, but maybe you've forgotten. It's kind of a quarter word, you know? Well, let's do it. Let's set this thing equal to 0. Let's see what happens. You know, maybe we can get a result and understand from the result what the word viable means. Right? So I subtract 4 from both sides. Maybe I'll multiply both sides by -2 to get rid of the -1/2. And I get x equals +8. All right. Why is that not viable? Take a look at this and take a look at this. It's not viable. Viable means realistic, usable. I'd say usable, viable. It can live on its own, right? That's not a viable answer because we only have values between 2 and 6. In fact, what's kind of cool, take a look at the graph for a second. I'm going to go back to my line tool here. If I took this line and I kept extending it, right, what would happen is eventually it would intersect the x-axis at 8. But the plain fact is, our function ends at 6. That's where it ends. That's also another great way of describing this, is just saying, look, the domain only goes up to the maximum x value of 6. This exceeds that. So it's not viable. Viable means usable, realistic, an answer we can use. All right, last question. What parameter, that's another important word, what parameter in the piecewise linear model indicates that the function is decreasing between x equals 2 and x equals 6? So from 2 to 6, the function is decreasing. What parameter in the linear model indicates that? Pause the video now and think about how to answer that question. All right, well, it's this. Parameters. Parameters are constants in mathematical models that affect the behavior of that model. And there are two things that really affect linear models that we've looked at in this course: the slope and the y-intercept. What controls whether a linear model increases or decreases is the slope. So specifically, the correct answer for this problem is the negative, actually let me put the word the negative slope of -1/2, right? Or we could even just say the slope of -1/2. that would be okay too. The plain fact is when slopes are negative, functions decrease, and when slopes are positive, functions increase. That's sort of the reason that we have slope and rate of change, right? Is to tell us whether a function is increasing or decreasing, and by how fast. All right, I'm going to clear all this out, so copy down anything you need to. All right, here it goes. Okay, well that was our last demonstration video. We hope that these videos from Units 1 to Unit 11 will help you get a sense for what we're going to have for you in the fall of 2014. All 100 lessons will have a video for them. And these videos, these lessons, and these homeworks will hopefully serve as a backbone for a Common Core Algebra 1 course that can be used in New York State and other locations. We hope that if you're a teacher watching these videos, that you'll join us, that you will contribute activities and ideas and edits, that you will do the lessons and tell us what went well and what didn't go well. We can make these lessons a part of the biggest lesson study that has ever been created, and the Common Core gives us a chance to do that. We know that these lessons basically lay the groundwork for a good course, but they're not a good course all by themselves. What we need are further enriching lessons and activities and projects that will go with this, and we invite you to join us on that journey. We're going to be working hard in the spring of 2014 to get an answer key produced for the eText and to get more videos made. We'll put some later. We'll put some videos on later out this. We'll put some videos later on out this spring. I can't talk anymore. So watch for them, but the bulk of them will be coming at the end of the summer. Thank you for joining me. This has been another Common Core Algebra 1 lesson. I'm Kirk Weiler. And assuming I can't garble my own name and my own sign-off phrase, keep thinking and keep solving problems. Thanks for joining us. Bye-bye for now.